Okay, well, thank you very much.
You're welcome.
Yeah, it's nice to be able to speak to you today. I understand this is like a craftsmanship or technical crafting track, but what I decided to go and speak to you all today about is something which is kind of like the intersection between the technical and the social. And sometimes you may have seen this term, socio-technical. And what I'm going to be doing here is basically talking a bit about, I think, like the mathematics and the forces involved in how software and human systems go and interact with each other. And I think this is vitally important because one of the things that often we don't really appreciate is that that there's system dynamics that really are underneath both social and technical systems. And as developers, we're basically dealing with these dynamics all the time. But quite often we don't really understand them as well as we should. Just a side note as well, just recently I basically joined the company Globant. This is a different thing for me, so it's nice to be part of this company and kind of move forward and speak to you in that capacity. So let's go and start from the very beginning. One of the things that is very common, that people quite often, one second, excuse me. One of the things that's interesting from a systems point of view is that there's this concept called isomorphism, which if you haven't run into this word before, I can explain briefly what it is. It's essentially when you have something which has roughly the same connection structure. So for instance, in graph theory in mathematics, you can have two graphs that may look very, very different from each other, but they may actually be isomorphic. And what this means is that essentially there is a mapping between the nodes and edges that is equivalent in the two different graphs that we have. Now, this may not seem to be a very significant thing. It looks like a mathematical thing that has no connection to the real world, but it really does. For instance, here, I can show you this graph, and maybe I can go and ask you this question. Is this the microservice dependency structure of an organization, or is this the team structure of an organization? Now, I won't tell you which one it happens to be because, frankly, often they look the same, and it's at a very deep level. That there are certain graph structures that repeat themselves in social realm and in technical realm, and not just in software development, but in all sorts of systems. And if we're able to understand the forces behind these things, we have more to draw upon when we're doing our work. So let's go and talk about something that's an example, very concrete, because we were just speaking now about mathematics and how that is universal. But this is a situation that I ran into a while ago, visiting an organization. They had this interesting problem where they had 6 teams, and these 6 teams all had the need to have an automated testing framework for doing their acceptance testing. And they looked and they tried to find something that they could use well. But what they discovered was that there wasn't anything that would work with the interfaces that they had. So they decided to make their own. So they made their own. And we can kind of like imagine it being here. This is like the testing application that all 6 teams used. Now, the fascinating thing about this is that they ran into some trouble. And I remember looking and seeing the trouble, and it looked kind of like this. When you looked at the testing application in the center, there was one public class that had many blocks of methods. These blocks of methods, functions, were all for the different things needed by the different teams. And it was kind of fascinating because I looked at this code first, and I didn't even know about the 6 teams that were involved in things. But I could still tell by looking at the code that there was a problem in the system, and the problem was beyond the code. So what we kind of did, if I go back to this a bit, is there is this issue of kind of like we have the testing application in the center, and it has code that looks like the code I just showed you. And then there was this thing of like, how do we solve this problem? The problem really, it seemed, was that there was no dedicated team for the testing application that was used by these 6 teams. And that's the superficial way of going and looking at the problem. But I think it's important, though, to go and just look at this and see what are the dynamics going on here. There was no dedicated team. People would go and work on it periodically and then go away. And you can look at this and say, well, what is the solution? And one solution might be, why don't we go and create a dedicated team for this testing application? But I really want to go and take a step away from this for a second first, before we dig into this problem, and try to understand the dynamics around this. Because once we do, we can see that there are actually many solutions to this problem that we just outlined. So I think the first thing to discuss is this core idea that was first developed by Mel Conway back in the 1970s. He made this observation about teams and also software structures. What he said is that when organizations build things, the team structure ends up becoming mirrored in the structure of the software that's being produced. And you may have heard of this before. If you have, I don't want to spend too much time explaining it. It's good for you to look this up if you want to go into more detail than what I just am about to explain. But I will explain the reason why this happens. What happens is that when you have different teams, it's cheaper to go and communicate inside the team than to communicate outside the team. And when this is true, then it seems like what has happened is that, that you're in a situation where to make code change, it's easier to change your local code than to change the interfaces between your stuff and other people's things. So a very natural thing that happens is that when you have three teams, the problem ends up being separated into three different pieces. And then different teams work on the different pieces. And what's amazing is that this will happen even if people didn't decide to go and have separate areas of code and separate teams. If they just separate the into three separate teams, then it's going to end up sort of like having that same kind of structure mirroring inside the software that's being produced. So this is an interesting thing to recognize. And once you see this concept, you'll find that you can basically sort of use it to understand systems all over the place. So there is this sense in which code and team structure are isomorphic, meaning they have the same shape, the same connection structure. And we can ask now, what are the other forces around software development that we can understand in order to inform better design decisions? Another one which comes in place is something called the Pareto distribution. And what this is basically something that's quite often referred to as the 80-20 rule, meaning that in some types of systems, sometimes even work, for instance, when you are performing a project, it seems like 80% of the work happens in the last 20% of time, for instance. And the other thing that happens with this too is that, this also applies to many other things like airport hubs, income distribution, various different things. To give an example of income distribution, in a market where there's no cap on salary, for instance, you will have a small number of people that earn very, very lot, and then a long tail distribution of people going to lower salary levels. And this is just a slide going and showing what this looks like for professional golfers, that there are some that have very, very high prize, and then it goes down to a lower level. And the same thing happens, as I mentioned earlier, with airport hubs. When you have airports across the country, when there is a hub, meaning a place that has many connections, people tend to go and actually connect to the hubs that have the most connections. And this is really the dynamic that occurs within the context of these distributions. There's the notion of preferential attachment, meaning that if something has more, we choose to attach to it, or we seek value by connection. So it just became the case in the continental US that one of the most connected airports is Atlanta. And then once Atlanta is very connected, other airports say, oh, should I have a flight from this airport to another small airport, or should I connect to Atlanta? Because once I do, then my passengers can go to many, many more places. So this structure is something that happens all over the place. It happens in income distribution. It happens just about any place where you start to discover that there's value differentials in things. Now you might ask, what does this have to do with software? Here I am talking about airports, right? But in software, this actually happens all the time, right? An interesting experiment that you can do is you can basically look at your software system, and if you have some tool that gives you the length of methods in a big project, what you'll discover is that generally they follow the power law distribution. So to draw the slide back here, you will have a very, very small number of methods that are very large, and then you have lots and lots of methods that are very, very small. It tends to have the same shape in this distribution. The same thing is true about class size, okay? The same thing is true about the in degree and out degree of dependencies. You will have some hubs that get much, much, much connection. And it's interesting about this because then we have to think, how does this happen? And I think what happens is that the areas of code that we concentrate on the most, that we change the most, are the ones on our mind. So when we think about where to make a change in code, we think about the places that we've been before, and then we make them bigger and bigger and bigger. That same shape right here, that also applies to commit frequencies within the context of a project. There's a small number of files in any project that receive most of the commits, and then there's lots of files that have like maybe 1 or 2 commits. So this is a thing which is an interesting way of going and looking at phenomena in the world that tends to apply to many things. So there's an interesting thing to think about with this as well, which is what would you really expect in terms of a good project, for instance? I mentioned earlier that in any project, you're bound to have only a small number of methods that are very, very large, and then lots of smaller methods. What if you decided that you wanted to make things better by going and refusing the check-in of any code where the method goes beyond maybe 15 lines because you don't want methods to be too big? You could do this, but then you end up having something which is like distortion. And that's what this slide is showing. This is like a picture of the waveform of a musical instrument. And you'll notice how it's flat on the top and flat on the bottom. And that's what the waveform looks like when there's distortion. When you cut the top and the bottom off, it sounds like distortion, okay? So the same thing is true when you're working in software. And in fact, I've visited teams where they had tried to have hard limits on the size of methods. And then, without me even knowing this, I was able to look at the methods and say, there's something wrong. The names are not matching the methods. They look like they've been changed in a way that doesn't make sense. So there is a natural shape to software, and it's important for us to see that. Now I want to switch to something else, which is really more about culture. One of the things that happens quite often in software organizations is we don't want the idea of like a coding hero, the person who takes too much work and basically sort of like ends up going and we become too dependent on this one person in the team or these 2 people in the team. But what is fascinating about this is that there have been some studies done that basically show that this happens all the time. There's this paper that came out earlier last year that basically describes for open source projects what the shape of the distribution is in open source projects. And the thing that they discovered is that for almost any large project, there's always a smaller number of people who are basically doing more commits and more contribution on the project. And then there's like a long tail of people that are not quite as involved as that core number of people. And we might look at this and go and say, oh no, we're going to have the cultural problem of people doing too much and then we're too dependent upon them, and then they think that they're great people that can't be argued with, and that's a terrible culture to go and have. But the thing that they said in the paper that was fascinating is that this power law relationship holds only as the teams go and get bigger. When you keep a small team, like maybe 4 or 5 people, then the dynamic is such that people are doing more even work and benefiting from their work a lot more. It's an interesting thing as well that what they discovered with this is that the people who were doing most of the work on these projects, their commits were actually of higher quality. And it's strange with this because I think when we look at this from the point of view of culture, we want to think that these people are kind of being mean. They're doing too much work. They're pushing other people aside and trying to do all the work. But I think that there's a natural thing that happens with this, which is that when you get into an area of code and then you make some changes and then you become the person that people kind of go back to over and over again, when there's a change there, then the amount of work that you do grows in that system. And this is, again, that preferential attachment thing that we talked about earlier. And we should not be surprised that essentially when there's a smaller number of minds working on a system, the quality goes up. So this is a dynamic that is useful for us to think about in development systems. So there is this concept that essentially we have limitations as human beings to how much we can actually handle when we're going and dealing with systems. And this concept is all around us. One expression of this is something called Dunbar's number. And this was first expressed by a man named Robin Dunbar. And what he was explaining with this was that it seems like for any person, you can only remember by face and name about 150 people. And they've done studies to see that this seems to be the case. And then this is, when you think about it, this is one of the reasons why, as companies grow, you have to change the internal structure of the company. Instead of being just one group of people, you have to break into subgroups in order to go and basically make things work. And that's because our cognitive structure is such that we can only work with a certain number of people at a time. So there is this thing, these cognitive limits are really physical in a way, not physical like this, but like physics, and that they vary from person to person, but still we can draw averages and understand just roughly when people are being overloaded and when they are not. So yeah, there's a thing with this as well to go and talk about, something that I think is fascinating. It's called Galileo's scaling law. And this has to do with the general issue of scaling. Galileo, who basically lived in the Middle Ages, he made an observation that for any structure that we have in the real world, the physical world, the volume of that structure grows faster than the surface area, okay, of the structure. And for this reason, we will never have a mouse that is as big as an elephant. If you had a mouse as big as an elephant, gravity would squish it because the weight of the volume is so big and the structure of the mouse's skeleton and its skin cannot actually handle that structure. Whereas an elephant probably has the right shape to be that size. The same thing is true about buildings. You can never build a skyscraper, a giant building, using the same materials as a cottage or a small house, because the structure has to be different as we grow. So we should not be surprised that architecture for us has to go and change as we grow things as well. So structure must change as things scale. There's more that we can kind of draw from within graph theory as well. One of the fundamental ideas in graph theory is the notion of a clique. And a clique is basically some subset of nodes or vertexes within a graph that is complete in the sense that everything connects to everything else in that small group. This is an interesting thing because this dynamic happens in both software development, both in software and also in teams. For instance, I don't know what this is like in Spanish, but in English, a clique is sometimes used in a way to go and describe like when you have 4 or 5 friends and then you're all together as friends and you want to keep other people out of your clique, right? So there's groups of friends that can be mean to each other, for instance. And so sometimes when there's a sport like football, for instance, there's always this thing of like you have a big team, but then there are some groups of people who spend more time with each other than others. And what's interesting about this is that we can see this in the social realm, but the same thing happens in the context of software because of the same force, right? I'm not talking about the being mean thing, but there is this sense in which there's a certain limitation when we start to go and grow structures. So imagine this. you're meeting with some friends at some party or something, and you decide you're going to go to a restaurant. If it's only 3 friends, it's very easy to decide what restaurant to go to. What happens when it's 15 friends? It takes longer, right? So this is a very typical thing that happens in social groups. And it's funny as well because dependency structures like this happen for us within software. Whenever you look at some big class, for instance, and this is pretty small as big classes go, you will find fields and methods that are more related to each other than they are related to other things. And this is very, very important because quite often these clusters inside the class structure can be things that you can extract out into separate structures. And a lot of refactoring is about breaking big things into smaller things. But to do this, we can look at the dependency structure. And actually the graph structure that we would see in graph theory of dependencies will show us these things. So it is interesting, when you look at social groups, big groups tend to become unstable and want to break into smaller groups. In software, these groups start to form, but there's nothing in software that basically goes and actually extracts them out into other classes. We have to do that work, okay? But we have to recognize that the reason we do that work is because there's a tension there. The tension is how much work is it for us to understand, and also the tension of the connectivity, which is related. Same stuff happens in biology, okay? If you have a cell, how does a cell divide? You have the cell, and then the nucleus starts to break in the center of the cell, breaks into 2 nuclei, and the entire cell splits. In biology, structure tends to break into smaller structures as it grows. So it's all the same thing. So yeah, there is this notion that what we refer to as the single responsibility principle. It tends to fall apart as we scale. And what I mean by this is that as things grow, they take on more responsibility, and then it becomes time for them to break into smaller pieces. Many of the things that we see as problems in software development actually disappear when we basically keep things very, very small. But we can't always do this. Many times we have bigger problems, and then we have to find a structure that works to go and solve the bigger problem, either in software or in teams. So yeah, there is this issue, and we've gone through this in the industry quite often, this notion of should we have teams that are dedicated to one particular area of the software, or should we have teams that can touch every other area of the software and basically work on one feature end to end? And I don't think there's any one right answer. I think there are tensions either way that we do this. When we have component teams that are focused on one particular area, one danger that we can have is that people start to pay so much attention to that area and they don't really see what's outside of it. And when we have these feature teams that can touch any area of the code, they don't feel the ownership of the code in the same way. And so they can end up making the quality suffer in ways that they don't even really notice because of the fact that, that they don't have the deep knowledge of that particular area of the design. So managing this tension is kind of important. And I said, there's no one right answer for this. To go back to that issue of the cliques within software, there's this old book by Frederick Brooks that talks about that tension specifically. There's something called Brooks' Law, where he says that adding people to a late project makes it later. And what this is really about is essentially, you know, just this interconnection tension. And what it is really is the notion that if you have n people and they're all able to talk to each other, then there are up to n squared connections between the people. And n squared grows much faster than n does. So every time you add a person, you're going and ramping up in a squared law way, the number of connections possible. So that's why things slow down, and that's why, you know, things can kind of go a bit crazy. This same tension of dependency happens in software. When you have many different components, it's good to have less dependency between the components of the software. As you add more components, you can add more connections. And those connections can often get in the way rampant dependency can make change very hard in software systems. So this leads to an interesting question. Can we become productive by scaling down? Let me show you what I mean by this. Well, it seems that when we confront the forces that make software development difficult, one of them is basically the fact that often we're looking at a lot of code, we're using many tools, and we have many people on our team. So it's almost to me as if we could make an equation for this, where we have these factors, F0, F1, F2, and I don't know what these numbers are, but if we say that there's some factor we can multiply times the number of people on the team, the number of tools we use, the number of lines of code that we have, maybe with the right factors, that should be below some number n. We don't know what that number n is, but we do know that all of these three things, the number of people we interact with, the number of tools that we use, the amount of code that we have to look at and understand, all these things are the things that kind of get into the point of us overloading with what we are doing. And it also leads to process problems sometimes. So maybe the solution is have just one person, right, who writes all the code, who basically uses just one tool, right, and keep the amount of code very small. That's kind of like a very ideal case, but as I said, we don't live in that ideal world often. So what we do is we basically try to go and keep team size at a particular level where it's manageable. A thing we have more trouble with now is keeping code size to the point where it's manageable. And you remember the 80-20 rule I talked about earlier? About 80% of the code is used about 20% of the time. This power law dynamic happens there also. So I would love to see in the industry a move towards going and just getting rid of dead code, or actually making the choice to get rid of code that doesn't have as much high value as other pieces of code. Unless we do this, then our code just increases and increases over time. And so does the dependency, and things start to slow down. Here's an interesting counterexample. There's a friend of mine, Ben Rady, and he wrote a blog back in 2017. And one of the things he talked about is how on his team, he had exactly 2 developers. They were working for people that were in the same room. Basically, they required software every day because of the work they were doing. There was no backlog. The 2 developers wrote code, together every day, pair programming. They wrote tests for everything that they had. If one was sick, the other person was there, and they both handled the ops support for things. So it's kind of funny what he just pointed out is that it's amazing how much process is really there just as a side effect of scale. And that's an interesting thing for us to recognize. And yeah, even if you can't go and if you are working on bigger projects, to the degree that our graph of relationships has fewer connections, better off sometimes in terms of going and segmenting out the cognitive space that we need to do our work. So, we try to manage this in many different ways. The early Spotify model was really all about matrixing things. So essentially, as a developer or a person in the company in development, you're part of a tribe, you're part of a chapter, you're part of a guild, and you're part of a squad. And essentially, you wear these 4 different hats, in order to participate within the organization. But then there's this question as well, how many hats can any one person wear, right? And I think the main thing I'm trying to get across here is that these complications are things which kind of like we need to understand the cost of these complications so we can select which ones give us the most value. Kind of moving back a bit, there's a French philosopher of science who basically worked on something on the socio-technical stuff I mentioned earlier. His name is Bruno Latour. And one of the things that he kind of described was something called actor network theory. He wrote about it in this book, Reassembling the Social. And it's very hard to read, at least it is for me, because he uses a lot of terminology that is common in the social sciences. But his idea was to be able to understand systems. What you need to do is you need to be able to go and look at both the physical things and the people and see the connections between both of them together. So if you are going to try to go and map out this system, here you would basically see there's you with the books that you read, and the weather and how that impacts you and the computer that you use, the power system. See all the things that can affect each other. And I think this unified view of the people, the things that we work on, and where the dependencies happen to be is a useful thing that we can use and also use as a basis for modeling things. So let's go back to the example I gave a little bit earlier, okay? We have this testing application in the center between 6 different teams. And we had a tension there, and the tension there led to that very poor code. What kinds of things can we do to fix this? Well, immediately, I think one thing that happens for most of us now is we are so used to thinking about the people space. And this is good because for a long time in our industry, we did not think about the people end of development as much. Now we think about it a lot, and that's very good. If you look at this problem from a people point of view, you might say, well, what we need to do is we need to go and have some people that are dedicated to working on this testing application. And maybe that would work out okay. Is there a cost for this? Yeah, there is a cost because then you have like more coordination. You have to coordinate with those people to get things done. And as well, it's kind of like maybe there isn't enough work to support a full team there. So that's a cost. But we can kind of go and look and see what the other possibilities are. Maybe we can go and have some people that just sort of like move in there and do things, the same people each time. They live on their original teams, but then they basically kind of go and they work on that. They become the dedicated person to work on that application by itself. So I show a graph here which shows like almost the frequency with which we actually have people working on the application that's in the center of this. That's one possibility as well. The other thing that we can do as well is, number of other things. I put here on the right explicit interfaces. And what I mean by this is that you can set it up so that rather than like say using inheritance in the center of this, we create like a plug-in architecture so that every team's able to go and use an API and plug in what they need for testing. So maybe some design would solve this problem and you wouldn't need a team maintaining this, but they wouldn't be dumping all of their junk into the base class that we talked about earlier. So that's another solution as well. Separate team, we mentioned already. There's a third one, which is called incorporation, which is kind of like, well, maybe this shouldn't be shared code at all. Maybe the code that we have there should be stuff that basically each team will go and get a copy of that repository, incorporate it in their repository, and then be able to go and work with it and modify it any way they want to. And then there's no common code in any place at all. So which one is the right solution? I don't think that any one of those is the right solution. But I think that if we use this kind of like, graph theory approach, what I'm calling socio-technical modeling, we're able to go and see what the dynamics are. And then based upon that, we are able to go and brainstorm and think about possible remedies, both in the social world and the technological world. And when we see those, then we can go and trade off all the possibilities that are there. And it's just a valuable perspective to go and have when you're going and confronting development problems within an organization. And I think the other thing I want to go and mention as well is that this thing of going and seeing the same forces manifest in many different systems, once you see that, then you begin to go and have what you have then is a very powerful tool for understanding all kinds of systems. And you can actually go and borrow ideas from one system domain to another once you understand these system characteristics of that. What happened in this case, back in that original team, is that there were basically two teams that made copies of the testing app and brought it into their own individual teams. And the rest of the teams decided to go and maintain that testing app, but they worked on a plugin interface for it. So they found a solution that works for everybody. And there were 2 different solutions. Isn't it good though that when you model things like this and then have as a separate step brainstorming solutions, you find more than one. And then sometimes you can even use both like this. It's rather powerful. So yeah, I think there's an underlying dynamic here, which is important to recognize. And I know that some of you watching this probably know of me from my work with legacy code. I've spent years working with teams that have lots and lots of code that requires testing and extensive work to go and make it more refactorable and suited for development. But a thing that I've kind of realized is that there is this sense in which the code and the team are one thing, right? And when we choose to go and separate them a bit, then when we think about them as being separate, then we get in trouble. And after all, what is legacy code really, except for code that doesn't have the same team with it all the time, right? If the team changes too fast, if it changes faster than the code, then you can be in a situation where nobody understands the code. If the code grows to be so big that there aren't enough team people to understand it, that's a problem also. So there's a subtle set of dependencies between the code and the people in an organization. And we need to be able to see these in order to be able to make good choices. Another thing to mention now is props. And I think this is another interesting thing to think about in the context of development. You'll see here that this building is being held up in a rather bad way, right? We do the same thing with trees sometimes. The tree is going to fall, so we kind of prop it up. Whenever you're thinking about adding a piece of structure or process to a development situation, one of the things that's important to recognize is what problem are you solving specifically? And also think about, when you do this, are you creating another problem also that you'll have to go and deal with later? And this is a very powerful way of going and looking at things. To give you a small little story about this, back in the earliest days of agile software development, when we were going in first, trying to practice extensive testing with unit testing and test-driven development, I remember seeing people that were working on a very big project, and they were kind of amazed because it felt like they could make lots of progress now because the tests were telling them whenever they broke existing behavior. And one of the things that they realized was that the tests were actually being used as a prop in a way. And basically they were able to make lots of changes without really understanding the system fully any longer at all. And that's kind of scary in a way. So we solved this problem of having systems that we have, that are hard to change, by introducing tests to make it easier to make the changes when we don't understand things fully. And then what do? We make bigger systems, and maybe we still can't understand these, right? So I don't have a particular answer with this, but I think that there's that thing to mention, that whenever you add structure or process, think about the problem you're solving, think about what other problems you could be introducing. Some of the things that we basically encounter all the time are because of the fact that we aren't thinking about those particular things. So yeah, I think that's an important thing to think about, is how much load can we handle? How much can we actually do? Architecture within systems is not just about software at all. And I think it's actually a shame in a way that we basically go and think about architecture as purely just the software systems of an organization. Because really the organization itself is part of the architecture, okay? We have all those relationships. And this is what Conway's law tells us, right? It might seem very strange to you if you look at this, and I don't want to talk too much about Globant. I'm not selling anything, right? I just joined or anything. But the thing I do want to mention with this is that when we were thinking about titles as I was joining, I specifically chose the title architect because I think that within the Agile community, we kind of minimize architecture a little bit, or we haven't placed it at the highest level of what we think about. We think about it as being an emergent thing that happens between teams of people, and that's all very good. But I do think that we can call that architecture too, not just design. The architecture of systems is vital. The architecture of the organization, the architecture of the code, all these things. And I think I'm pretty much done with this. I just wanted to go and sort of relay these things to you, and hopefully you get a chance to look at the slides later. Send me email or anything like that if you have questions. But I think there's a lot here that you can use to track down lots of information about how these forces work in software development. And the benefit to doing this is becoming a much better designer, because you can kind of see where things are going. Okay, so yeah, I just want to go and basically end on the note that these are all natural dynamics that happen in systems. And the more we know about them, the better off we are as we change things. So now I guess I'll just kind of open it up. And if there are any questions at all that can either come through the chat or through the interpreters, I'm fine to go and answer questions too. Thank you very much.
Thank you. Si alguien tiene alguna pregunta, y la puede escribir en el chat y la leemos. O abrir el micrófono, como quieran.
Michael?
Yes. Hello? Thought I heard somebody.
Well, there's a question on chat from Daniel. He would like to know, what do you recommend to avoid working as silos?
Avoid working in silos. Yeah, it's funny. One of the things I kind of recommend a great deal is actually people moving from team to team. Okay. It's something which isn't really a common practice within the industry now, because people are often thinking about teams gelling so that you have a fixed membership of the teams in such a way that you can all get very focused on a problem. But the danger with that is that you can get into a situation where you're not seeing external perspectives at all. So I like to see organizations have like a rotation policy sometimes, where you almost like you're doing a tour over your career, going from place to place to place. And it's interesting with this because you have to think about, what does that look like from a management perspective in an organization? But there's great benefit in this. I've heard of one organization where they discovered that over time software quality was going down, and they didn't even, the team members weren't even aware of it because they were just so used to seeing the code all the time. They just knew that they understood it. When a new person joined the team, they were lost because they just didn't have all this background knowledge. So spreading knowledge and perspective throughout the organization by having people move from team to team periodically is a very valuable practice.
Maximiliano has another question. Should the same team developing features be on call for handling errors or bugs?
Can you repeat the question one more time?
Yeah, should the same team developing features be on call for handling errors?
One of the things that we like to do as much as possible is remove the handoffs from one team to another. So it is an ideal thing, but the other thing about it too is that we all have to sleep, we all have to eat, we all have to live outside of our work as well. So it seems inevitable for any application that's going to be running 24/7 that you'll have some separate ops that happens as well. It's funny. I think we have to really balance our human needs a great deal with what the demands of the system happens to be. So there's a benefit to being, on call if you're a developer and understanding those things in the system. But there's also the other issue as well, is that we can't all be on call 24 hours. It doesn't work all that well.
Andres, would like you to tell a story.
Okay.
Using one of these, you can pick one. The first option is regular expressions. The second one is recursion. And the third one is encodings.
Encodings? Yeah. So you're asking me to tell a story?
Yeah.
Oh, I don't know. The one thing I know about regular expressions is the joke about regular expressions, which is I had a problem and then I basically used regular expressions. Now I have two problems. Okay, which is like an old joke around. Regarding stories, I think regular expressions is a fun one because it's a very terse notation that allows you to do many powerful things. But it's like this crazy space that I find myself in where I write the regular expression. I definitely want to have tests to document what it actually matches once it gets to a particular level of complexity. So I've spent time doing that kind of thing, actually testing regular expressions. And then sometimes what I do is I actually go and throw away the test and break down the regular expression into smaller pieces so that my mind can understand what's really going on with it. So there is that tension between small and big and also understandable and not understandable that's related to regular expressions. Hope that works as a story. So.
Yeah, he's laughing. So
Okay,
I think it
good.
worked. Federico would like to know, what do you think about tools that measure classes connections and dependencies?
I think they're great. I think it's one of those things that you should be paying attention to. A lot of times developers just really kind of know already what's going on with that, but if there's a tool that's around that you can use to go and discover these things, it's great. The one thing I would add to this though is that having the tool is one thing, but another important thing is to go and find the hotspots in your code and make a team or organization plan about how you will approach change in the hard areas. And I don't see enough teams doing this. If you have a massive area of dependency and it's changed often and it's valuable code, then maybe you can say on your team that nobody touches this without sitting down with some other people and making a plan for it. Okay. And then, of course, the other areas people are free to change. But you have to figure out what's the most valuable code that you have, what's the code that's changed most frequently, and what's the most complex code. And when all three of those things are true in an area, you need a plan that you basically use every time that you modify that area of code. And that's just the way to go and keep things going well.
There's another question from Maximiliano. How do we handle tech debt in the click? Can you give us some tips?
Handle tech debt in the click. I'm not exactly sure with I'll talk about a bigger click maybe. It's a thing I don't have in this presentation, but there's a thing I call quality views, which is a very interesting thing, which is actually creating a diagram where you have the different parts of your system and you use colors to go and indicate which areas have the most technical debt and refer to those during the planning process. Doing this so that basically people understand when they're selecting features, what is being impacted in the code. And then you can choose whether to go and actually do those things right now or do them later when they're in a better state, all these things. I think that a lot of technical debt that we have is a side effect of, making decisions about what work we're going to do next without paying attention to what the state of the system really is. Because if you know that particular area of the system has some structural trouble and there's a way of avoiding that work then and basically fixing it first, then you're in a better situation than you would be otherwise. So the click part, I guess I'm answering with this, is that I think a lot of technical debt comes from miscommunication between business and development. And when there's a freer communication about those things, and when we actually raise the concerns we have in software in the planning process, then we can make better decisions and hopefully avoid more technical debt in the future.
There's a question from Omar. Is there any metric or model that allow us to visualize these dependencies between software processes and people?
Yeah, there is. I'm on the advisory board of a company called CodeScene. And so I don't like being like, oh, hey, this is a great product, but it's a cool product. It really is. The company was developed by, the product was developed by someone named Adam Tornhill. And I really recommend his books. He has a couple of books. I think it's like Software Design X-Rays or Your Code as a Crime Scene. That's one of the books also. And what he's basically done is he spent years going and doing repository analysis and basically producing graphical representations to go and kind of show, how all these things mix together. So I think there's evaluation copies you can use to go and sort of get a sense of, who has, where all most of the commits happening in the code base and various different things along these lines. And of course, there's Sonar Cube as well to go and sort of figure out a lot of these things, particularly on the complexity front. And I think CodeScene does complexity things now too.
Okay, so we have another question from Felipe. What relation can you see between this idea of not getting rid of the code and take a lot of the technical debt without a payback policy?
I'm not sure I understand the question. So not getting rid of technical debt and using a payback policy?
Felipe, would you like to open your mic?
Yeah. Sorry, can you hear me?
Yes.
Yeah, great. So that was just a way to say this word policy. The question is aimed to see how you see. I mean, I was this idea of the dev code and a lot of lines of code that are not being used in many projects, in many products. Which relationship do you see between the way we handle technical debt between those two areas?
The relationship between the policies and the system?
No. The way we handle technical debt, that many times we take technical debt, but we never end up paying that debt. Let's say we don't handle that. We leave it there, as we also leave that debt code. Yeah, no, you're right. It's a very similar thing like that too. It's really kind of hard to get people to spend the time to just get rid of dead code. It's really, I don't know how to make the best case for that yet. I do know with technical debt is that it is also hard to go and pay it down. I guess the key thing with it really is the hotspot analysis I was talking about earlier, because when you're doing that, at the very least, even if you're not paying things down, you're putting yourself in a position where you're not making it worse. And that's great. The other thing I'll bring up in terms of that as well with technical debt, and it's the thing I always mention when we're working with legacy code, is that you only have to go and put a class in a test harness once. The hardest work is breaking dependencies to go and get coverage on a class. And because of that 80-20 rule, you'll find over time that areas of code that you've changed before, you'll come back to them and discover there's already tests in those places. And that's a really powerful thing, that recognizing that in a way your code base isn't as big as you think it is. If you're writing tests as you make changes to code, you're going to end up covering the hotspots of your code over time. And then your work is going to become a lot easier. So yeah, paying down technical debt is tough. You can do it by going and figuring out what the core domain is. Eric Evans' work with domain-driven design is a very powerful reference for that. Yeah, it's really a matter of going and making sure things don't get worse and making sure that everything is livable going forward within the code base.
Okay, thanks. We have our next speaker in the room, and we need to rearrange chairs and clean up the room a little bit. So thank you so much, Michael, for
Thank you. It's
this
been
session.
fun. Thanks a lot.
Okay. See you soon, I hope.
Yes, definitely. Take care.
You too. Bueno, para todos, gracias por estar en la sesión. Si alguien se queda a la próxima, les pedimos que vuelvan a entrar en unos 10 minutos más o menos. Así acomodamos un poquito las cosas.
Bye. Thanks, Michael.
Thank you.
It was a pleasure.
Yes, definitely for me too.